reiterate at least one point that I made on the video before we get going, because honestly, this is kind of a theme of not only this class, but to be honest, like all physics. Somebody remarked to me once, and we were like first year grad school, and they were like, dude, you know, the whole first year of a PhD program in physics is just, we do orthogonal functional decomposition and call it physics. And he was right. So this idea that functions and can be expressed in different bases is really ubiquitous, really important, and actually really profound, because in some sense, what the physics question, whether it be, you know, quantum mechanical or electromagnetic, is kind of asking you is, what's the best basis? Like, in what basis does the answer just fall like a ripe apple off of a tree? And you started this idea with just vectors, you know, and you've got a vector, and maybe the question is something sliding down an inclined plane. And, you know, at this point, you have kind of this reflexive idea that like, oh, well, I'll just ask what coordinate system should I best express all of the force vectors. So now we're going to kind of do that with functions themselves. And the kind of invitation I made was, yeah, fine, there's some function f of x, and maybe it like wiggles, and it's doing something more complicated, but let's just think about it at a few points. Call this f1 and f2 and dot, 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 fn. And fn is its value at xn, and likewise f1 is its value at x1. So you can totally, in some sense, think of this vector or this function as a form of a vector. And you can write it in the way that we're kind of used to writing vectors. And I'll call this xk hat with x hat k equal to this sort of goofy looking thing that has a whole bunch of zeros until we get to the kth element, and then it's got a 1. And these things, the xk, definitely satisfy the requirements for a basis, namely that xk dot xj is equal to, hopefully everybody gets it by now, third time through, our favorite symbol.
Delta kj.
Exactly. So the Kronecker delta. So when k equals j, we get 1. When k equals not j, so when they're different, like 2 and 3, we get 0. So that's a basis. And you're like, that's really dumb, because, you know, what I'm doing in some sense is the function itself, f of x, has an infinite amount of information in it, and you're representing it discretely. Well, that's not dumb if you end up taking a job or wanting to represent things digitally, like sound or pictures. So in a sense, you're pixelating a real function. And so there's enormous practical application in doing this. And also you can imagine that, well, as I let n go to infinity, I actually get a better and better representation of this function, especially smooth functions. So if you ever want to teach a computer how to do physics, it's enormously practical too. So not a bad idea at all. And now our question is, could we use different bases? To represent functions? Like the whole thing. And the answer is a resounding yes. And in fact, you guys already know one. I think this gets taught for you guys at the end of Calc 2 for some reason, or maybe Calc 3, like as a weird extra unit. You're used to seeing the first term of this, but you do have an example in the form of Taylor's theorem. So the Taylor or Maclaurin series says that f of x, if f of x is differentiable smooth technically. All the derivatives exist at some point or in a neighborhood surrounding that point. That fk is 0. So funky notation, the k in brackets means the kth derivative. So we take its value at some point and then we look at how far away we go from that point. So what this is, if you think about expanding this term, so that's just like a polynomial. So essentially Taylor series or Maclaurin series are, you know, already an example of you doing this. You're representing anything. It could be like sine to the 4th power divided by e to the sine of x or something like that. You can represent that as a Taylor expansion, which is a polynomial expansion because those are polynomials. So we'll call this a polynomial basis. And the basis actually gets like super quotes because we haven't shown that basis functions are, or polynomials are true basis functions. And some are, some aren't. So we'll get back to that when we talk about like Legendre polynomials and stuff. But anyway, this is the bigger picture, is that the Fourier series is a great example because it's pretty well behaved of representing functions in terms of a different basis. Okay. So that having been said, here is Fourier's theorem. I need a periodic function f of x, and then I can represent it on some basis or on some interval by a sum of sines and cosines. And then we may as well write the representation. And to be honest, this is just one way of writing the Fourier expansion. We'll get to a cooler way involving exponentials, maybe even by the end of the day. Okay, so there's f of x, and here is the whole thing. So f of x equals a naught over 2. There are also different ways of writing this. I think this is one of the clunkier ways, but at the very least, it parses out all the terms, so it's kind of easier to look at it at first and see what's going on. So you have an infinite number of cosines. It's a pi. And each one has its own personal coefficient, tells you how much of that particular wiggle to use. And we have an infinite number of sines. Okay. And t is the period of this periodic function. So this is, for starters, we'll use this, the Fourier series, for periodic functions, except not really, but we'll get periodic answers. And the important part about this is that, you know, sines and cosines, you know, we've got them in our memory banks, we've got them programmed into calculators, in, you know, in math libraries, in Mathematica, or your favorite programming languages math library. So really, in a sense, what this is saying is, if you tell me the a's and the b's, I can represent the function, which is pretty cool. Okay, so I'll go back through all the demos at the same time, but what we didn't do in that video is we didn't talk about how you actually make the a's and b's, and so that's basically our first goal today. So any questions about the idea of the Fourier series? Or any questions about how this is possible, or maybe what sort of functions? You know, you can think of some pathological functions that shouldn't satisfy this, and you might be right. So you haven't put any conditions on the nature of f of x yet. Can anybody actually think about a type of f of x for which this seems like something that shouldn't work and probably doesn't work?
I mean, some kind of like discrete function that like jumps all over the place with no period probably has a pretty messy Fourier series.
Yeah, so discontinuities will be an issue, because I don't care how many sines and cosines you add together, like how would they jump from one point to another? So in fact, you can use this on a discontinuous function, and we will a lot because those are the easiest ones to learn how to use Fourier series on. They just have a particularly fine but incorrect behavior at the discontinuity. So discontinuities are definitely a problem, but they're bad in a well-behaved sort of way. So that's nice. Yeah, we'll have a whole list of stuff, and you can like kind of let that simmer on the back burner for a while. Okay, so where do these A's and B's come from? So the A's and B's, in some sense, really extending this vector analogy. So let's say that I just wanted to go back to talking about taking some vector A, and I had it ax I hat plus ay j hat plus a z k hat, and now I want to turn it into some new basis. I mean, it's still the same vector, a1 e1 a2 e2 a3 e3 hat. So these coefficients, actually all of them, come from the same process. And you can do it either component-wise if you know the components, so that kind of defeats the purpose, or you can do it geometrically. Is that ax, for instance, is a dot I hat, right? Very clearly by just examining the formula. Now what you would have to do in practice maybe is you would have to say a cosine of the angle in between, a and the x-axis, for instance. So same thing here, if I want to go into a new basis, ak, my new component in that basis, is equal to a dot ek. And if I knew the components, well, I wouldn't really need to be doing this. So I would probably more likely take the magnitude of a and then calculate our old friends, the direction cosines. Right? So that's the angle in between a and that axis. So it turns out this is kind of how Fourier stuff works, is that we need an analog of the scalar product, or dot product, or inner product for functions. Because in some sense, our analogy is this, is that the EKs are going to be turned into these sine and pi t x's, or cosine and pi t x's. And we're going to need some coefficient out front to make sure they're the same size. And then the vector we're trying to represent, that's f, the function itself. So dotting these two things on the left-hand side together is going to be like seeing how much of the f of x overlaps with the sine or with the cosine. And for functions, the analog of a scalar product is what's called an inner product. And there's more than one. You'll see other ones probably at some point in your life. So we will kind of motivate and define an inner product. Which just means that two functions go in and just a number comes out, as essentially, if you think about dot products in between a vector, I don't know, what haven't we used? Let's just keep using A and B. I'm uncreative. So, whoops. So we're done talking about this in beautiful abstract generalities. Now the question is like, no, I actually want to do this. So I'm in some d-dimensional space. I want to compute, and dot product, I just multiply the coefficients together, right? So now I want to look at this function f and this function g, and I want to inner product them. Well, maybe that might look something like this. We might sum over k from 1 to n, f of xk, g of xk. And then we might want to take a limit as n goes to infinity. And what is this starting to look like, actually?
Probably an integral.
Yes. So it turns out that an integral really is a thing that is very analogous to a scalar product. So you can put a weight on it, like some additional thing, but for us, our first so-called inner product of functions is going to be the integral over some predefined interval. Might be -1 to 1, 0 to pi. For this, it'll be 0 to the period is probably the best way of doing it. And then f of x, g of x, dx. And you might even see notation that looks like this at some point in your life. But we won't use that in this class. We'll leave it for quantum mechanics. So essentially, the overlap in between two functions is given by multiply them together and take their integral. Okay. And in fact, sines and cosines, yeah, it sounds maybe like it's miraculous, but this is the work that Fourier did. Who, by the way, was a lunatic. Like, Fourier would wear 10 coats because he didn't want his life essence in the form of heat to escape his body, which is kind of crazy. So think about that the next time you're like using the fruits of the Fourier series, like your
You just get hotter.
MP. What's that?
You just get hotter, wearing like multiple jackets.
Yeah, I don't know. Like, I don't know how he like personally felt about it. I think he lived in like southern France too, which is like pretty damn warm in the summer. But yeah, he had this like weird theory about losing heat, so he would bundle up even in summer. He's sort of a crazy person. But at the same time, he also did a lot of work on things like the theory of heat transfer. So, you know, maybe he was onto something. Okay, yeah, let's just clear everything. So with this idea of our inner product as an integral, we can see that the sines and cosines have basis-like properties, which is say like we're almost there. All we have to do is put coefficients out in front of them, and they satisfy basis properties. So let me remind you guys, like, this is what we want. We'd like ek.ej to be equal to the Kronecker delta. What does that mean for sines and cosines with this inner product? It would be cool if for our periodic functions, so our interval 0 to t, sine of 2 pi m over tx, so that's the thing in one of the things in Fourier series, cosine 2 pi n over t. So these are different coefficients. So let me color code them. So this is an m, and this is an n. So what would you like this to be? So this is kind of a, yeah.
Oh, I was going to say, if it's like the Kronecker delta, then hopefully there's like a condition that makes it equal to 0.
Yes, so in fact, these are going to be 0, and this is worth staring at. So this is the role of the t in the Fourier series, is that when x equals t, I get 2 pi m or 2 pi n. So essentially what this thing downstairs, if you go all the way back to like your pre-calculus theory of functions class, is that this thing's role is to scale the sines and cosines so that every time you get to t, so when m equals 1, it's 2 pi, so that's the period of sine. When m is 2, it's 2 pi times 2, so 4 pi, so this thing has repeated twice. Because m and n are integers, what's going to happen is I have 1 period, 2 periods, 3 periods every time I get to t. So I have a sine over its full period and a cosine over its full period. One's even, one's odd. What happens when I multiply an even function times an odd function and take their integral?
You get 0.
Yep. So always 0. So this is free actually for like all m and all m. So for all m and n, which is a reminder are integers, positive integers. I think the symbol for that, that's like n with the plus on it, but we're a physics class, so who cares? Okay, so that's great. So that's really Kronecker delta-like. The next thing I should check, and the thing that again is a little bit funky, is we have 2 different functions. We have sines and cosines. And by the end of the week, next week, we're gonna get rid of that too. So now I have 2 pi m, and I can stop highlighting the different colors because you know they're there. Sine 2 pi n tx dx. Okay, so what would you like this to be? And this one's not necessarily obvious. So it would be great if this was Kronecker delta. The problem is sines, so sine squared integrated from 0 to pi doesn't quite equal 1. So we've got a little coefficient that we have to deal with. So in fact, this equals t over 2 times mn. And again, m and n are any positive integers. But it's got the Kronecker delta part. That's good. And likewise, without belaboring the point, cosine 2 pi m over t cosine. So mixed sine and cosine, they vanish because of odd-even symmetry arguments. But if you take one of the odds and one of the odds, or one of the evens and one of the evens, they almost do Kronecker delta stuff. And this is actually worth, next time you open Mathematica, exploring and making sure this is right. Take 2 different sines with 2 different periods, and then integrate them over one of their period multiples, like I'm saying here, and then verify that this is actually true. So this is great. This is almost a basis. So in some sense, what we can conclude from this is that with a little bit of putting something out in front, so root 2 over t cosine 2 pi m over tx, and root 2 over t sine 2 pi n t over x. Do what we want them to do. They're orthogonal to each other, and they're normalized. And that's what the role of the root 2 over t is that now when I multiply this thing times itself and then integrate from 0 to t, I get 1 instead of t over 2. So these are our basis vectors, and these are the things that we'll use to dot product to get a's and b's. So any questions about that before I write that down and then we just start trying to use it? Okay, so finally, so now we got coefficient formula, which is this, and now you know where this 2/t thing comes from. And honestly, just the same thing, swap out sine for cosine. And these are for the positive values. So k equals 1, 2, 3. And then a naught, which has a special role, gets kind of dealt with separately. Does anybody recognize this formula? Maybe like the third theorem that you
Like
learned.
center of mass or something?
Yeah, totally. So it's in a pure calculus setting, it's the mean value theorem, but for a physicist, what you'd probably think about it is the location of the centroid, so the center of mass. So this is the center of mass of the function, exactly right. And the reason this exists in the Fourier series is because sines and cosines over a full period or 2 periods or 3 periods, their average is 0. But we didn't say all of our periodic f of x are 0 average functions. So in a sense, what this does is this lets you represent functions with an average value. Okay, I will write one note about this, is if you truly are representing a periodic function, you can do this, is you don't have to go from 0 to t in the integral. You can use whatever limits you want, as long as it's an entire period. For example, if we're just going to talk about a function that's periodic with period 2 pi, this set of formulas would tell you to integrate from 0 to 2 pi, but the function itself is periodic, so you could use minus pi to pi if you wanted to. You could use 0 to negative 2 pi. You could use minus pi over 2 to 3 pi over 2, as long as it's an entire period. So the reason to do that is maybe some of the limits are better behaved than others, for instance. Okay, what'll happen in practice is a lot of times you'll use Fourier series for non-periodic functions. So as much as we like to talk about orchestral music, is that a violin playing, strictly speaking, isn't really periodic. You know, it starts and stops at some point. Okay, so those are the formula. Stare at them, write them down, appreciate them, ask questions about them, and then we'll use them in probably one of the easier things that I could come up with, just so you can see all the mechanics. Okay, good. So we had a rectangular wave as an example in the pre-lecture video, whatever you want to call it. So let's compute that one. And the rectangular wave looked like this. it had a period of 8 and it spent half its time at 2 and half its time at 0. So call this f of x, and there's x, and then 4, 8, 12. So in, probably contemporary all digital signal processing, you probably wouldn't Fourier series this. You would just have, rectangular waves are really easy to represent in terms of piecewise continuous functions, for instance. But anyway, it's a nice one to integrate. So we need an actual mathematical representation of this. So the actual mathematical representation of this is that it's 2 when x is in between 0 and 4. And some of the subtleties of these limits will sort of matter. And when it's in between 4 and 8, it's 0. And it's periodic with period 8. So any point at 8 to it, you should get the point itself. Right. So that's the piecewise representation of this function. Okay, so again, what we need is we need all the A's and all the B's. Can somebody tell me what A naught is? I'm prepared to wait because you can do this the hard way or the easy way.
Would it just be 2, our first function?
So close. So it's the average value. So, but yeah, it's just going to be the thing that offsets it. So you're thinking about taking a sine wave and you've got to like add something to it to move it up from the x-axis probably, right? What is the average value of a function that spends half its life at 2 and half its life at 0?
So it's 1.
Exactly. Okay, the other way of thinking about it is visualize just a sine wave. And a sine wave goes in between -1 and +1. Where would I have to shift that sine wave so that it started looking like this? I would have to add 1 to it to move it so that it kind of looks like this. Okay, but I don't believe me, so I'm going to compute this anyway. So the formula itself would say this is what I have to do. 1 over period, integral 0 to period. I can shift this if I want, but I don't really see any reason to. In this case, f of x dx. So period is 8. Integral from 0 to 8, f of x dx. Well, this is a piecewise continuous function, so I've got to split it up into its 2 pieces. So from 0 to 4, f of x dx plus 4 to 8, f of x dx. Oops. And from 4 to 8, the function is 0, so that's gone. So we're left with 1 over 8, integral 0 to 4. It's 2 dx, so that's 2x dx, so that's 2 times 8 divided by 8. Oops, 2 times 4. Okay, so that was the hard way. The easy way is what's the average value of whatever this thing is. So if you actually have like a super goofy function, unlike the one that we have here, you would actually have to do that, but it is good to verify that this checks out. So that's the average value. I like the version where you did no work to get that though. Okay, what we did do by doing that is give you guys the template for finding the rest of these, like how the calculation would actually work. So tell me what ANs are. And what should happen is there should be an N left in your formula at the end of the day, because the ANs will be different sizes. You know, I might have more of a low frequency component and I might have less of a high frequency component. So give that a shot. Because this is a constant function, you won't have to do any integration by parts or anything like that. I'll warn you that that will happen on a homework problem. And then we'll check back in like 2-3 minutes, I think is reasonable for this. Anybody finish? Should be mad at me if you got the right answer.
This is 0.
Yeah.
Okay.
Okay, why did I know this was 0 before I started doing work? The A's are the coefficients on the cosines.
Yeah. F of x is an odd function and cosine is an even function.
Exactly. So we could have done, this is the nice thing about Fourier series in some cases, is you threw away a million coefficients by just realizing the symmetry of this. So yeah, it should be 0 because cosines are even functions and our function itself is an odd function. So it kind of looks like a clunky sine that is shifted up by 1 unit. So we should have sine terms, shouldn't have cosine terms. It's just kind of like a, some intuition. But we'll do this anyway, because it's going to be warm up for the B's, which, after putting you guys through that, I will do. So f of x cosine, okay, the 2 and the 8 give me a pi n over 4x dx. And then I now have 1/4, it vanishes, the integrand vanishes from 4 to 8, so I'm just left 0 to 4. 2 times cosine pi n over 4x dx. And then if I wanted to do this the hard way, I'd pull this out, I get 1/2. And then what's the antiderivative of cosine? Well, that's sine. And then I'm going to get some gunk out front. So let's do that, put that here. And I'll do that later. Of pi n over 4x evaluated at 4 and 0. And then just to do everything on the up and up, we should have 4 pi n. So that will not vanish next time. And we have, okay, evaluate this, put in the 4. So I get sine of pi n, where n is an integer. So sine generically at pi, 3 pi, 2 pi. So always vanishes, and then sine of 0 always vanishes. So in fact, this always vanishes at n pi for n positive integer. Okay. So that is a big old 0. Won't. Okay, we'll abuse some board work and we'll try to get the BNs by changing as little as we need to. So now you want the BNs. The BNs are just changing cosines to sines. So now I want the BNs. This is sine, sine, sine. All of the rest of the argument we made, the fact that f of x vanishes on the first half goes away, but now what we ask is what's the antiderivative of of sine, that's negative cosine. Okay, well, what's negative cosine evaluated at 0, that's -1, and what's negative cosine evaluated at pi, 2 pi, 4 pi. So half the time we get 1 minus minus 1 when n is odd. So that's asking about cosine, so -1 minus 1, right? And the other half of the time we get -1 plus 1 when n is even. So half of the time it vanishes as well, so we get +1 minus 1, and the other half of the time we get minus minus. So I distributed the minus from the minus cosine. And then overall what we would get is 4 pi over k times 1/2 times 2. So half the time this equals 2, half the time this equals 0. So what we're left with is Bn. I went a little bit quickly through that. So even if you missed a detail, the idea of what I did makes sense. So cosine of 0 is always equal to 1, and there's a -1 out in front. And then cosine of pi n is going to be equal to either +1 or -1, depending on whether or not it's 2 or 3 or 4 or 5, even or odd. Okay, so then we get b of n is 4 over pi n. Okay, we had an infinite number of coefficients to determine, and 3/4 of the infinity disappeared, so we still have infinity. And this is it. So if you want to represent this rectangular wave, all you would have to do is walk up to somebody and say, Fourier series on the interval 0 to 8, a0 equals 1, bn equals 4 over pi n, and they would make this wave. Okay. So any questions about any of that? So I'm going to spend the next maybe 15, 20 minutes going through Mathematica, because we've now earned the right, especially after that nasty zero integral, earned the right to do this in Mathematica instead. Okay. So as a last note, I will say as a practical point is that these are the types of integrals that you'll see when using the sine and cosine Fourier series. And so it really just honestly comes down to evaluating integrals of the form f of x sine x. So just as a primer for the homework, if I wanted to compute an integral that looked like this, or cosine instead of sine, what would I do? The technique that I would use if I wanted to do that by hand. Ye old desert island physics. So integrating just straight up sine by itself would be great. So it would be cool if there was some technique that took a derivative of one of the terms inside of an integrand. So this is just primed for integration by parts. And if somebody gave you something like this, a whole polynomial, this would be integration by parts k times. And that would also mean that they really don't like you and respect your time. But if you do have to do one of these by hand, that's basically the technique, you would use. Okay, so as I said, we've now earned the right to go to Mathematica if nobody has any questions about what's going on overall. And really importantly is using the symmetry of the function you're expressing to save yourself a lot of work. Okay. So here we are. You guys see the Mathematica worksheet? Okay, I'm gonna do one by hand because we made this, and then after that use the functions that Mathematica comes with. So again, this is like a partial sum. So this one is our A naught, and then this command says sum stuff up, and then this says 4 over pi n, that was the coefficient bn that we computed, and then we got only the signs that are going to contribute. And so we're going to sum this up to some final number. Okay. So this would be the, oops. So this would be the first partial sum, and then this rectangular wave itself. And let's go the same interval that we did this on in the example. So let's go in between 0 and 16. Okay, so what you can see is two things that actually didn't show up in our discussion, but were mentioned. So this function has a discontinuity at the points 4 and 8 and 12 and 16, where it just magically jumps in between 2 and 4, teleports. You can see what the Fourier series is doing here and what the Fourier series is going to always do. So in fact, it will always give you the average value. So here it's at 1. And this is because the sine or the cosine is a continuous function itself. Okay, so this is just one term. We added the one outside, so technically this is two terms, the constant term and then the sine. And then if I add some terms, you'll see this gets more and more high frequency wiggles and does a better and better job of approximating this. So I'll give you guys this code to kind of mess with at the, as a basis for solving some of the homework problems. But thing that wasn't mentioned in the last videos, this is what it does with discontinuities. It takes its average value. Okay. I will just take the Fourier series of some function, and actually I'm open to taking requests because this isn't something that we're really prepared to talk about at the moment. This will be next week. Give me your favorite function and we'll see how Mathematica Fourier series is it. So typing in the chat is also fine if you don't want to try to dictate it. Okay, super gross. That's a great one. Because I have no idea, in fact, what this thing is going to do. So we'll do ln x over x. Great suggestion. And I've got to stay away from it blowing up. So let's see what it does. Yeah, it doesn't even want to evaluate it. Oh, sorry. Log, that's why. It's thinking. Okay, this is awesome because I think this crashed the kernel. So let's do one thing that might make life easier. Let's move this 1 unit away from the origin. So actually, let's do 4 because I don't know if the standard interval for this is minus pi to pi or minus 1 to 1. And I can smell my laptop cooking, so let's stop this. Oh yeah. So it should have better luck with this, but still no guarantees. Logs are sketchy. Yeah, I'm surprised Mathematica doesn't throw an error, but what this is a good example of is what is this function doing that is not a good candidate for a Fourier series? So this will be one of the, so discontinuities, it won't get the answer right, but it will give you an answer. However, blowups are not okay for a Fourier series. So one of the three conditions we'll put on this is the function needs to be absolutely differentiable or absolutely integrable. So here we've got a blow up at 4, and here we've got a blow up at 4 as well. So definite issue. Okay, so let me get something that I know will actually. So excellent example, and we found one of the things that Fourier series will not do. So let's just do a silly little polynomial or something like that. Let's do x to the x squared. And what this is saying is give me the first 4 terms. Okay, so it's okay with that. What do you notice about this output? Do you see a collection of sines and cosines? You see e to the ix and 3e to the ix. So this is a more elegant way of writing the sines and cosines through Euler's formula that we haven't covered yet, but we will by the end of next week, just because going straight to the complex plane when you're still wrapping your head around Fourier series would be kind of rough. So what you guys should be able to do and understand, like kind of beginning to end, is Fourier sine and cosine series. So these will return the first sine coefficients and the first cosine coefficients, and both of them will include a naught if it's got one. So the Fourier sine and cosine series, and then I can plot them. So does that look like x squared? Not particularly, but maybe if we add some more terms, it might get a little better. Okay, it gets a little better. Maybe if we add more terms, you see where this is going. So sequentially better approximations, and uglier might look better. Okay. So last thing I'll point out before we get back to the full Fourier series, and that's next week, like what's going on with the e to the I whatever instead of sines and cosines, is this thing has a default range to be expressed to express the Fourier series. So I think it's -1 to 1. What would happen if I change this from -10 to 10? So visualize what you think this thing would look like if I extended the range that I plotted my Fourier series over. Okay, so somebody with a better processor and Mathematica kernel than I did. Yeah, so Mathematica will compute the first terms of ln x over x4, so that's good.
It's
Probably not ln x itself. Yeah, it's a mess. Cool.
Yeah. You have to scroll down to see the whole thing.
Yeah, this I'm using like an old burnt out laptop that I feel comfortable installing Zoom on, so it's probably not going to do anything that's actual work. Yeah, if it does ln x over x, I'd be actually really impressed. So it would know to change the interval away from the place where it blows up. Yeah, yeah, that's cool. Okay, so this is the standard interval when you use Fourier series. This is what Mathematica assumes that you're looking at. Oh my God. Yeah, that's awesome.
How to read that.
Yeah, the point is it's all, oh yeah, so it's expressed in terms of, yeah, the Euler gamma formula. Yeah, this is really good stuff. We get a hypergeometric function and then some Euler gamma formulas. Okay, the point to note from this is that these are all nasty functions, but they're evaluated at specific points. So those are all numbers. They're gross numbers, but they're numbers. And then they're multiplying a sine or a cosine or an e to the I. Yeah. Yeah, that's good stuff. So we'll actually see a lot of these functions by the end of the class. So you guys will see the gamma function and hypergeometric functions. So that's something to look forward to. Yeah, gamma and beta are pretty cool. Okay, so let me extend this beyond the interval that we originally defined. And then what you see is, aha, so this is another limitation. So you can take the Fourier series of functions that are non-periodic, but the sines and the cosines are always going to give you a periodic answer. So essentially what we did is we took, and this looks like the interval, yeah, this looks like minus pi to pi actually is the standard interval. So this is periodic over the interval minus pi to pi. So you'll always get a periodic function out, even though you don't necessarily put a periodic function in. Sometimes that's okay. We can change that by changing the Fourier parameters. So now I'm going to change this sum, and I'm going to, you know, my laptop at least, I'm going to stay away from the natural log of x minus 4 divided by x minus 4. So let's just do x squared again, but I'm going to change the interval over which I represent this to minus 4 to 4. Actually, let's go a little bit goofier and let's do 0 to 10 and see what happens. So if I want to do 0 to 10, should I use a cosine series? So I'm using not an even interval, so I should not use an even function. So this seems more like a job for the Fourier sine series. And we'll see if this works. So it's going to think for a while. It doesn't look so bad. And then I'm going to plot. Extend some x. And then we'll try the same thing. So these are also kind of a long form way. And you see that these look very different, right? So this is a long form way of, in some sense, saying that there is no such thing as the Fourier series of a non-periodic function. You would have to say, like, I'm doing this over one particular part of the range. So if the function itself is periodic, it has a Fourier series, and that is always going to be the integral over that period. But if you want to, and there are reasons to do it, express a non-periodic function with Fourier series, realize that you're to some degree choosing how you're going to represent it. Okay. So any questions about any of that stuff? So I'll provide you guys with this code, but it looks like at least some of you have it figured out well enough. Cool. So yeah, it's like 11:20, so may as well, if there are no questions, I will publish the quiz. And we can start a little bit early, so you guys have time to scan before getting to the next class.